On a quiet laboratory table lay a thin, silvery wire. At first glance, it looked no different from an ordinary piece of metal. But when a student bent it into a sharp angle and then gently heated it, something astonishing happened. The wire slowly straightened itself, as if it had a will of its own. This strange behavior belongs to a class of materials known as shape memory alloys SMAs, often called smart metals. Unlike ordinary metals, which deform permanently when bent, SMAs can recover their original shape when exposed to heat. The question is, how can a metal remember anything at all? The answer lies deep within the atomic structure of the material. At the microscopic level, metals are made of atoms arranged in highly ordered patterns called crystal structure. In shape memory alloys, these structures can exist in two different forms: a low-temperature phase called martensite, and a high-temperature phase called austenite. When the alloy is cool, it enters the martensite phase. In this state, the crystal structure is flexible. Instead of breaking when bent, the material accommodates deformation through a process called twinning, where regions of the crystal rearrange in an organized way without destroying atomic bonds. This is why the metal can be bent easily without permanent damage. However, the key lies in what happens next. When the material is heated, the atoms gain energy and reorganize themselves into the austenite phase, a more ordered and stable structure. During this transformation, the crystal lattice returns to its original configuration, and as a result, the entire object regains its initial shape. In other words, the memory is not stored like information in a brain. It is physically embedded in the atomic arrangement of the material. But where does the original shape come from? Before use, shape memory alloys undergo a process called training. Engineers heat the alloy to a high temperature and set it into a desired form. This process establishes the stable austenite structure, the shape the material will always return to. From then on, no matter how many times the material is bent in its martensite phase, heating will drive it back to that trained configuration. Recent research has pushed this phenomenon even further. Scientists have developed new alloys that function under extreme conditions, including temperatures as low as 200 C for space applications. At the same time, advances in artificial intelligence are helping discover new compositions with improved efficiency and durability, expanding their use in robotics, medicine, and aerospace. Shape memory alloys are used in everything from medical stents that expand inside the human body to aircraft components that change shape during flight. It becomes the most fascinating materials in modern engineering.